Test, test. Okay. I hope you had a very nice flex week and you have a good rest. And let's welcome back to class and let's start the second half of this term. And before we start today's lecture, let me quickly go through what we have for some updates of this course. And we have released the marks of assignment 1, and you can send us emails for a breakdown of your marks, like how many marks did you get for each question. And if you have questions regarding the why you got some marks deducted, but you think that you have done it correctly, then you can come to the help session and ask for explanations from our course admins. So we will be sending out notifications about these help sessions later. And by the end of this week, which means by the end of perhaps this weekend, we will release the specifications for assignment 2. And the deadline for assignment 2 is in week 11. So you will have around 1 month to do assignment 2. And for assignment 2, it's more about coding. So, hi. Pardon? You did what? Oh, you don't have it yet. I think maybe you can let us know. You can check with the course admin here about your marks, because we have marked all of your assignments, but maybe the system takes some time to display some of your marks. So you can check with our course admin here. We do have a backup, a copy of your marks somewhere else, apart from the school's system. So you don't need to worry about that if you can't see your mark yet. So, but if you still cannot see your mark by the end of this week, you definitely should come to us and we will look into the problem there. So, okay, so let's continue to our lecture content today. So today we are going to learn about software complexity. So this is today's outline. We will go through an overview of software complexity, and we will go through 3 different levels of complexities. We will go through the unit level, the integration level, and system level. And we will learn different metrics of calculating software complexity. So first, when you see this term, complexity, it is somehow familiar, right? When you were learning algorithms, you have learned complexity, right? So we have learned, when we learn algorithms, we have learned there are different complexities for searching algorithms. For example, we have the time complexity. We have learned the space complexity for these searching algorithms. And we have these notations marking the complexity of these algorithms. Like O1 means the complexity is constant. On means it's a linear complexity, and n square means it goes like a square. So these are the complexities used for these algorithms, but they are not usable for measuring the complexity of software. And that is because these complexities are computational complexity. So they are used to measure either the time we need for computing something or the memory space we need for computing something. but they don't measure the complexity of the structure of the code. So that's the key difference here. So it is, so you may have learned this concept, but although the name is the same, the actual concept behind the term is different. So let's have a more detailed look at this, the difference here. So for computational complexity, it is actually used to measure the resource required for doing certain calculation. And so it is used to check the efficiency of these algorithms and whether these algorithms are feasible for larger inputs. But for software complexity, it is different. It is used to measure the structure of the software system, and it is used to help with thinking about how to understand how difficult it is to understand the software, to maintain the software, or to update the software. So it has nothing to do with the actual computation. It has nothing to do with the actual computational resource when executing the software. It is only related to more like the cognitive part for the piece of code. So it only measures how difficult it is for human to use or to maintain the code. So this is the difference between software complexity and computational complexity. And because normally, why suddenly we have some echo here? And normally because it is believed that high complexity is associated with high risks of having bugs. So that's why we are learning software complexity in this course, because we are doing testing, right? We want to find bugs, and if we could identify which part of the software is more complex, then we can focus on testing that part of the software to find bugs. So this is why we need to learn software complexity in this course. Now let's continue to some metrics for calculating software complexity. And we will learn it according to different levels of the system, similar to how we learn different levels of testing. So first, we will learn unit level of complexity. And we will learn two metrics here. The first one is called cyclomatic complexity. So by definition, cyclomatic complexity could be used for calculating the complexity of any graph. And in terms of a control flow graph here, the formula is given as this. So cyclomatic complexity equals to the number of edge minus the number of n plus 2 times the number of subparts of the entire graph. So E here stands for the number of edges, N here stands for the number of nodes, and P here is the number of connected components. So basically, a graph could have multiple subgraphs, and each subgraph is considered as a P here. But normally, because we are thinking about unit level of testing here, so we only care about one particular method or one particular function. So normally for one function, we only have one connected part. So every subgraph is connected together as an entire big graph. So we don't really have subgraphs for unit level of control flow graphs. So P here is 1, it's just 1. So the formula could be simplified as e minus n plus 2. So we just use the number of edges minus the number of nodes plus 2 as the final number of cyclomatic complexity. So this is the formula we are going to use here. And let's have a look at an example of how to do this calculation. So let's consider this program. And you have practiced in assignment 1 of how to draw a control flow graph, right? So can you draw a control flow graph of this? So what is a control flow graph here? So it's pretty straightforward. We have two if here, two nested ifs, and this is the control flow graph. And what is the number, what is the cyclomatic complexity then according to this control flow graph? It should be E minus the number of nodes plus 2, right? So we have 4 edges, we have 5 nodes, and the final number of complexity, cyclomatic complexity is 4 minus 5 plus 2, which is just 1 here. So it is pretty simple and straightforward. And let's think about, for a given program, which factors could affect the cyclomatic complexity of this program. So let's consider doing some variations for this very simple control flow graph. So let's say we add an exit basic block here. So does this modification increase the cyclomatic complexity here? Does it increase? No, right? Because we use, in the formula, it's like E minus N. So we care about the number of edges, new edges, and the number of new nodes. And in this update, we are bringing in one more node and one more edge. And if we do E minus N, then this update is kind of doing nothing here. So we're not increasing the cyclomatic complexity if we do this modification. And what if we change this return here, this return tool here, into a go tool, which means that we are having a loop here. We are looping back to this very first basic block. So will this increase the cyclomatic complexity? Yes, right, because we are not removing any nodes, but we are introducing new edges. So we are increasing the cyclomatic complexity here. So the observation here is, so what is increasing the complexity here? So actually the branches and loops are increasing the cyclomatic complexities because they are the sources of new edges or extra edges. So branches and loops are one of the factors affecting cyclomatic complexity, but they are not the only factor here. So let's consider this example here. So if we simply modify the program like this, are we introducing new but if we simply modify the program like this program is not really a valid one because we are actually lacking some exit point here, and we need to add some return basic blocks. And if we modify this program like this, are we increasing the cyclomatic complexity here? No, right? Although we introduced a branch, we are not increasing the cyclomatic complexity here. So introducing branches does not always increase the cyclomatic complexity. And it is not the only factor here. So if we further modify the program, sorry, I think, oh, okay. So if we change the basic block into one return instead of two returns, are we increasing the cyclomatic complexity? No. We introduced 3 basic blocks and we introduced 4 edges. So we are increasing the cyclomatic complexity if we do the update like this, instead of having 2 returns. So we can see that although introducing branches, if we just stop here, if we don't add the 2 returns, we are increasing the number of cyclomatic complexity, right? Because we, we are not. And if we reduce the number of returns, we are increasing the number of the cyclomatic complexity. So actually, returns and exits are also affecting cyclomatic complexities, and they have a negative effect, as we could see just now. If we have 2 different returns, we have less complexity here. So, and some online materials, they just ignore returns, which is wrong. But if you see them, you just ignore that. But they should consider returns here. So, according to what we have observed, actually, we can have a way of calculating cyclomatic complexity faster than having to draw a control flow graph and count the number of edges and nodes from the control flow graph. So we can skip the step of drawing a control flow graph if we know which factors are affecting the cyclomatic complexity. And the fast calculation here is, the formula here is 2 plus the number of ifs plus the number of loops plus the number of cases inside a switch minus the number of returns or exits. So this is the new formula according to the factors affecting the cyclomatic complexity. So let's have a look at this program again here. So we know that ifs and loops are, these type of things are bringing in new branches and returns are reducing. So this roughly explains why this formula looks like this. So, and let's verify it using this program here. So just now we know that using control flow graph, the cyclomatic complexity for this program is just 1. And using this formula here, so how many ifs do we have? We have 2 ifs, right? And we have no loops, we have no cases, and we have 3 different returns. So it's 2 plus 2 minus 3, it is still 1. So both formula will give us the same thing here. So this is how we can calculate cyclomatic complexity faster using this formula without really building a control flow graph. And let's have a live poll here today for the Jam Mark. So this is a program we have, and you are encouraged to use the fast calculation method to calculate the cyclomatic complexity here. So the formula is 2 plus the number of ifs plus the number of loops plus the number of cases minus the number of returns here. So the control flow graph of this program could be very complex or too complex to draw in a few minutes, right? But you can quickly calculate by counting the number of some special statements like the if or loop or return statements. So remember the formula is like this. So can you calculate the cyclomatic complexity for this function here? So it's like, it looks like this. Pardon? Yes. You have to make a guess whether how many cases should be counted here, like whether the default case should be counted as a case. It's a case by definition, but you should think about it because we count the number of ifs, right, in this example, but we didn't count the else here, right? So does this default, is the default the same as case here? It's not the same keyword at least, right? It's considered as a case, but it's not using the case keyword. So you can just make a guess because we are not really checking the correctness of your answers. It's just a practice. So, okay, I think most of you might have got the answer, and let's have a look at. So we have the same number of 6 and 7. Actually, the correct answer is 6. So default does not count here. And let's have a look at why default is not counted by looking into the details. So first, let's use the control flow graph to check the ground truth, to check the correct value of the cyclomatic complexity here. So the control flow graph is like this, and we just use the number of edges minus the number of nodes plus 2, and it should be 6. So now we know the answer is 6. And let's come back to the fast calculation formula here. So we have, how many ifs do we have? We have 2 ifs, right? And how many loops do we have? We have 1 loop here, this while loop here. And how many cases do we have? Actually, we only have 2 cases here. We don't count the default case. And we have 1 return here. So the calculation is 2. But you may wonder, okay, why didn't we count this default case? So we can think about one extreme case where this switch, this entire switch statement has only one default case. Let's imagine this entire switch has only, let's assume that we don't have the case 1 and 2, we just have one default case. Then this entire thing is just one basic block, right? It doesn't have any branch, it doesn't have any extra edges. So this default case actually works like else here. It doesn't bring in new edge. So cyclomatic complexity is about having more edges in the graph. So comparing to the number of nodes. So because this default case is not bringing in new edge, so that's why it is not counted. So if we think about this extreme case, so that's why we don't count the default case here. However, so you can see that cyclomatic complexity is quite easy to calculate, and it can help us to understand the structural complexity of a graph or of a given piece of code, right? We know how complex is the control flow graph of a given piece of code. And that's the advantage of cyclomatic complexity, but it has some limitations. Let's think about this program here, because cyclomatic complexity is an oversimplified metric. And let's think about this program here. So this program actually checks whether 3 given numbers can form a triangle or not. So we can use compound conditions here to just have one if and one else to do this check. And if we calculate the cyclomatic complexity is very low, it's only 2. However, we can also write the same program by decomposing this compound condition here. We can write write it with nested ifs, right? So we can write the program like this. And if we draw the control flow graph and calculate the cyclomatic complexity, it's increasing the cyclomatic complexity. But actually, these two programs are essentially the same. So we can see that one limitation here of cyclomatic complexity is that it only calculates the complexity of the control flow graph, but it doesn't count into the data flow. So it doesn't check whether, because we can use compound conditions to make the control flow graph look simpler, right? But it doesn't mean this program is more, it doesn't mean the program below is more complex than the previous one, because in in these compound conditions, we are equally likely to make mistakes here, right? So it doesn't really simplify the program. So cyclomatic complexity only measures the structural complexity of the control flow graph, and it doesn't consider the data part. That's the first limit. And the second limit is it actually ignores the code size, which is actually very important for finding bugs, because we can have a very large function, maybe with a few hundred lines of code, with no if and no else, and just execute sequentially this big function. We could have this scenario here. And this big function has a very low cyclomatic complexity, right? Because of the lack of branches, but it could be very, very buggy. So the second limitation of cyclomatic complexity is that it ignores the size of the code. So that's why we need some other metrics to measure the unit level of code complexity. And the second metric we are going to learn here is called house-types metric. You can infer from the name that this is actually from a person's name. So this one was developed by this guy in 1977. It's very old, but it is still used. It is still used. And by that time, and even now, it is still like this. So by that time, actually, programs were kind of written in some language similar to assembly code today. So programs are considered to be made up of operators and operands. So this metric is all about dealing with operators and operands. So it is based on the following quantities here. So there are some concepts here, and we will learn it through some examples later. But you don't need to remember everything in this slide right now. So, but we will go through this one anyway. So the first variable here used for calculating house-types complexity is the number of distinct operators, which is denoted as the lowercase n here, n1, and we also need to calculate the number of distinct or unique operands, which is also denoted with a lower letter n, but it is n2. And we also need to calculate the total number of operators, which is denoted with an uppercase n1. And we also need to calculate the total number of operands, which is n2 in uppercase. So based on these, we have several metrics for measuring the complexity or the size of the code. So the first one is program length. So basically, program length is the total number of operators and operands. So we just calculate n1 plus n2 in uppercase. So uppercase means total number, and lowercase means unique things. So the vocabulary in the vocabulary in natural language is like we only count the unique things, right? So the vocabulary is the total number of unique operators plus the total number of unique operands. Sorry, I just pressed the wrong button of this laptop. Okay, so the program volume is calculated like this. So it's the program length times log with 2 bases the program vocabulary. So it is defined like this, and the program difficulty is calculated like this. So we can, once we have these 4 numbers, we can combine them together to calculate different metrics. And we can also finally calculate the program effort, which could be considered as the final product here of Haussteid's complexity. But there are some other final products of this set of metrics, and we will learn them later. But I don't like those metrics, and I will explain why. So these metrics should be language independent, but they cannot avoid language features nowadays because it was proposed in 1977. And by that time, like programs are all written in something like the machine code or the assembly code. So everything could be considered classified as either an operand or an operator. But now we have, for the programming languages we are using today, we have many different language features, right? And it's hard to classify something as an operator or as an operand. So there are some language features affecting the classification of operators and operands. And here we provide some rules for C programs. And I won't read through all these rules in this lecture here because you can see it's quite overwhelming, but you can use this lecture slides as a piece of lecture note to check whether something is counted as an operator or an operand. So this is just for your reference. So basically, you just need to know that these rules are dealing with whether a keyword or something should be counted as an operand or operator. So that's it. And let's have a look at how Haussteid's metrics work with an example here. So remember, we need to count 4 basic things. So what are the operators in this program here? So we need to count the number of distinct operators, right? So what are the number of operators? So operators are things that are being operated, right? So M here is an operator. 3 here is an operator. Oh, but sorry. Operands are things that are being operated. Operators are the operators of the expressions. So sorry about it. And how can I remove everything? Erase all. Okay, so this smaller than is an operator here. So this plus equals is another, minus equal is another. This equals is an assignment operator. It's assigning value to k, right? So it's also counted as an operator. And this modular is also an operator. This divide is also an operator. And this plus is another unique one. Times is another unique one. And what else? We don't have more unique operators here, right? So these are all the unique operators. So sorry, if is also another unique operator. We omitted this if here. So these are the unique operators of this program here. And therefore, the number of distinct unique operators is 9 here. And then we need to count the number of occurrences of each unique operator. And then we will get this. So the total number of operators is 21. So for example, this equals appears 3 times, right? We just have 3 here in this table. And then the total number of operators increased by 3. So the total number of operators is 21 here. And let's have a look at the number of operands here. So the operands are the things that are being operated. So these are the objects here we have. So we have m, we have 3, we have 12, we have y, we have 1, we have k, we have 100, we have j, we have day of week, we have d here, we have m here, 26, 10, and k has already been counted, and we have j has already been counted. We have 5, we have 7, right? We have all these unique operators. So operands. So these are the operands here we have. So the unique number of operands is 15 here. And similar to how we count the number of occurrences for these operators, we can count the number of occurrences for these operands. And then we have the total number of operands equal to 25. And then we can calculate the rest of the matrix using these 4 basic values. So we can have the program length as the uppercase N1 plus uppercase N2. So the program length is 46. And we have the vocabulary as lowercase N1 plus or lowercase N2, which is 24. We can have the program volume calculated with these values. And we can also have the program difficulty. So this is how we can calculate these measurements. And of course, we should have the final product, which is the programming effort here. And actually, in the original House-Ted's matrix, the author proposed 2 other values we could calculate. The first one is time required to program. So it is calculated like this. So it is the programming effort divided by 18 seconds. That is the estimated time for writing this program. But we will see this is kind of ridiculous. I don't think this value makes sense, but it is defined like this in House-Ted's matrix. But I don't think it's real. And the second one is the number of delivered bugs. It's the number of program volume divided by 3,000, or we can use this formula to calculate the number of estimated bugs in this program. And as far as the actual bugs we find in the code is smaller than this estimated number of bugs, then this quality of the program is considered acceptable. So that's the basic idea of House-Ted's matrix. And let's come back to this example here to see why I think it doesn't make sense. So if we use the algorithm or the formula to calculate the time required to program this thing here is like 87 seconds. So I don't think if you could figure out the logic of the program, you don't need 80 seconds to type in everything here, right? But if we think about this big formula here, maybe it takes more than 80 seconds to think about this program here. So that's why I think the calculation of this time required to program is not realistic. And the number of delivered bugs is 0.07. But I think personally, I think this big formula here could be very buggy if you ask me to write this program. So I think these two metrics are not very usable, but the programming effort here could be used as a measurement of the volume of the entire program. So this one is still useful. But these two, you can just use it as a reference. It doesn't mean anything for real. So that's why I think we should just focus on using this programming effort here. And those are the unit level of complexity. And before we jump into the second half of today's lecture, let's have a 5 minutes break. And I'll see you at around 11:51. So, can he find the? Maybe let's solve the problem after class. So let's continue the second half of today's lecture. So just now we learned two unit level of metrics for calculating software complexity. And let's have a look at some integration level of metrics for this complexity calculation here. So the first one is because we know that complexity, cyclomatic complexity could be applied to any graphs, right? And remember when we learned unit testing and integration testing, when we learned different levels of coverage, we learned not only the control flow graph, but also the call graph. So we have learned it before when we learn different levels of testing. And we know that, okay, a call graph is still a control flow graph, but it is on a higher level. It is more focused on the connections between different subroutines. Basically, normally these nodes are just functions. So since cyclomatic complexity can be applied to any graph, we can also calculate the cyclomatic complexity for call graphs. So if we have a call graph for a particular program or a particular piece of integration of units, then we can calculate the cyclomatic complexity of that integration. And for this example here, the cyclomatic complexity is 6. So basically we need to use edge minus n plus 2 formula to do this for call graphs. We can't have the fast calculation. We don't have if, and we don't have while loops. We don't have the different statements here for us to do a quick calculation. So we have to use a graph here. And another set of metrics for integration level of complexity is the object-oriented complexity. So that's why object-oriented programming is one of the prerequisites for this course. But since this course is becoming a core, I don't want it to block your graduation. So maybe we will remove the requirement and let's just go through this part of the knowledge. And you just need to know that when you are dealing with object-oriented programs, you can use these metrics, but we don't learn them in details. So the metric here is called the CK metric, which is not the brand, the CK brand. It is related to two names, and it is one of the best known set of metrics for object-oriented software, and there are 6 metrics here, and you can roughly know what does each metric mean by reading its name. So basically, the weight methods per class is kind of related to the number of methods, right? So the number of child classes is literally the number of child classes and these things. But let's select some key concepts and explain with more details. So the first one is the weight methods per class. So the weight here we apply is actually the complexity of the method. So we don't count the plain number of methods. So we count the complexity of each method and sum them up. And that's basically the first metric here. And we can use cyclomatic metric complexity. We can use Hofstad metric. So it's just a sum of the complexity of the metrics inside this class. And we could also count the coupling between classes. So this is to check the number of classes which are related to a particular class, and this relation is bidirectional. So if that particular class calls this class, then this class is considered coupled with that class. And if this class calls a method inside another class, then it's also counted as a coupling here. So basically, we just count the number of classes that are coupled with this particular class we are looking into here. So this is the second metric here. And the third one we are going to explain in detail is the response for classes. It's actually calculated by adding the number of methods inside the class, except for the inherited classes, plus the number of distinct method calls made by the methods in the class. So it's basically how many responses from method calls we can have in this class. So as far as we are calling some other methods and we are getting some responses, and that method is not an inherited method, then it is counted for this class. So this is literally the like the number of responses inside this class we get inside this class. So these concepts are pretty much self-explanatory. But the last one is requires a little bit of comprehension, and let's have a look at the detail here. So in object-oriented programming, we have learned the concept of we are encouraging to have high cohesion but low coupling for our code, right? High cohesion means that we put similar concepts together. So this high cohesion and low coupling, they are kind of related in object-oriented programming. So high cohesion means we are putting similar things together, and low coupling means different things should be separated. So we are kind of modularizing our design of the code. So we can reuse some modules and we can replace some modules and update them independently in object-oriented programs. So this one here this metric here is related to how do we calculate the cohesion within the methods of a class. And it has 5 different variants, and we will only learn one of them here. So we learn the simplest one. So the simplest one is the steps for calculating this lack of cohesion here is that we start from listing all the methods and attributes of the class, and then we determine the relationship between the methods and attributes. So we just have a look at which methods are using which attributes. And then we evaluate method pairs. So basically, if 2 methods are related to the same attribute, then we pair them together. And then we can calculate the lack of cohesion on methods metric using the number of method pairs. So let's have a look at an example. I won't go through too much of details within this here. Let's use an example to explain this. So assume we have this class here, and we want to calculate the cohesion between methods inside this class. And in this class, we have 3 attributes, A1, A2, and A3. We have 3 methods, M1, M2, and M3. So basically, we can just list all of them here. And then we calculate the relationships between methods and attributes. So basically, M1 uses A2 and A1 and A2, and M2 uses A2 and A3, and M3 uses A3, right? So, and then we compare them together according to the shared attributes between these methods. So we can see that, sorry, the pen is, so we can have these pairs. So M1 and M2 shares a tool, so it's cohesive, cohesive. And M3 and M1 and M3, they don't share any attributes. And M2 and M3, they share A3 here. And then we have non-cohesive pair, which is M1 and M3, we have 1. And we have two cohesive pairs, M1, M2, and M2, M3. And we just use 1 minus 2 to calculate the lack of cohesive in this class. So you can see that from this calculation here, from this formula here, it is encouraging methods to share attributes of the class. So it means that basically it roughly means if more methods are using the same attributes within the class, it means that these functions, these methods are similar to each other and they are kind of cohesive. So this is the basic idea here. And there are different variations for this LCOM, and you can find a summary of this different variations here. And actually this, I just updated this link this morning and I found that the previous link was no longer available. It was actually from some materials from another university, but I don't know why they put it down. So I replaced this with a paper here. So you can, if you are interested, you can have a look at this detailed material here. So that's integration level of complexity. And now let's jump into system level of complexity. Actually, for system level, we don't have unique complexity metrics. We just use the same metrics as we are using for the integration level of complexities. So, but for system level of complexity, we do have some interesting knowledge to learn here. And there was a study in 2018, which is related to, is software complexity positively related to vulnerabilities or bugs, which means that if a piece of software is more complex, then is it more likely to be buggy or not? So this is the research question which is trying to be solved by this study here. And the finding is actually hard to tell. So we can hardly say that a more complex piece of code is more likely to be buggy or more likely to be vulnerable. It actually all depends on different situations and scenarios. You can imagine that even when you are writing a very complex piece of code, maybe you are more focused and you are less likely to make mistakes because you are paying more attention when writing the code, right? But when you are writing a relatively easier piece of code, maybe you just lose your attention. Maybe you are, having some typos, and it could lead to some bugs. So it's hard to tell whether complexity is positively related to bugs or not. So although in general people think that more complexity means more likely to be buggy, but this is not the case actually according to some research. And this is a research paper. If you are interested to have a detailed look, and they have many, many different tables, different data inside, but actually they have actually used many different prediction methods to check whether a piece of code is buggy or not. And these prediction methods could be very complex. They are using some complexity metrics. They are using some machine learning models or even some deep learning models. But most of the prediction methods cannot outperform by simply counting the number of like the volume of the code, like for example, the lines of code. So it means that more lines of code means more bugs. So we don't So this is the situation here. And the relation of software complexity, however, we are still learning it here. And because when you go to work in some companies, they have requirements on cyclomatic complexity per function. So they don't want you to write over complex functions in your code. So the relation with testing and fuzzing here is that we can still use these metrics, some complexity metrics, to identify valuable targets, because one of the method we have learned just now, like the house type matrix, is related to the program volume. Like it's a better version of counting the lines of code, right? So we can still use these metrics to calculate valuable targets, even though that we don't have scientific evidence showing that more complexity means more bug, but we can still use them to identify targets. And there is actually a practical tool here, which was developed by a guy in New York University. It is called Fuzzable, and as indicated by the name of the tool, it basically identifies the functions which are fuzzable, which could be applied for which could be used for fuzzing. And you can see that it has a fuzzability score, and this score is actually calculated with this. You can see that complexity or cyclomatic complexity is one of the metrics here. And if you wonder why it doesn't use house types metrics, it's actually because cyclomatic complexity, although it has several limitations, it's very easy to calculate. We can just, even use a stream matcher to match for if while loops, for loops inside the program to quickly calculate this cyclomatic complexity. So that's why it is used here. And that's all for the main content today. And let's continue our journey of learning PyTest. So PyTest is actually usable for your assignment tool. So that's why we are learning it. And because assignment tool will be more focused on writing some code. Although you have written some code for assignment 1, but we will write more in assignment 2. And basically, we will practice unit testing and integration testing and system testing in assignment 2. So you will be writing automated tests for this assignment. And this is to get you prepared with the actual library you are going to use for assignment 2. So in our last lecture, we quickly went through the concept of fixture, but I think you might have forgot about it. So let's have a recap of what is a fixture. So a fixture is actually used to provide reusable, composable setup and tear down for this for a piece of test. And you can see this in this example here. Let's use this with a larger font. So you can see in this test, sorry. So as you can see here, we have, in this test, we just read from a temporary file and check whether the file content equals to hello world or not. And if this file content does not equal to hello world, it will return an error. Otherwise, the test will pass. That's very simple. However, we can see that this requires us to read a file, right? This requires us to maintain a file in our test. And we don't want to generate many files, because in reality, we could write, we could have multiple tests, And we could have thousands of tests actually in some bigger projects. And we don't want to generate thousands of files and keep them there after running the test, right? We should have some process to create that file, and we should have some process to remove the file after doing testing. And this lifetime of setting up and removing files is actually handled by this thing called fixture here. So you can see that this file, this test function here, actually it accepts this temp text file, which is a fixture, which is defined as a fixture for this environment. And inside this fixture, we can see that we could have a piece of setup code which can create the file. And then we could have a piece of tear down code which will remove the file. And we have a statement here called yield, which will pass the file we just generated to the actual test using this fixture here. And we will learn why are we using this keyword yield instead of return here. And this is roughly the structure of this fixture and this test. And let's have a look at how it works in action. So we just run pytest.v, and we can see that this test has been passed. And if we look at this folder, we can see that there's no temporary file created, right? Because we are properly setting up the file and we are properly tearing down the file. And to verify this, what we can do is we can try to comment this tear down 2 lines of tear down code and see what will happen if we run the test again. We just commented these 2 lines of code, and if we run this test again, you can see we are still passing the test. This is a little bit annoying. And if we run the test again, we can see we can still pass the test because we are doing the setup and test correctly. But if we look at the folder, you can see the temp file was kept there because you can see it has hello world inside. And that's because we are skipping the tear down process. So the fixture is actually helping us to write clean code for setting up the environment and tearing down the environment for doing testing. And we can use both yield and return in this fixture here. So basically the fixture is to return something to the actual function that is going to use that thing and that environment object. So that environment object could be either a file or a connection handle of some web clients. So you may have learned the keyword yield in Python, and it is a little bit different from the usage of this keyword is a little bit different from how we use it in normal Python code. So basically, if we use return in the code, it will terminate the execution of the current function. So if we use return here instead of yield, it's actually skipping the entire tear down. So it's basically the same as how we comment out this tear down here. So return will terminate the current function. However, yield will not terminate the current function. It will just suspend the execution of the current function. So, and normally the return value in Python, the return value returns just the value, and yield will just give us a generator object instead of the actual value. And we can use that generator object to do something. And if we can use this program to practice or to recap to recap what the keyword yield test. No, not test. Try. So you can see this in this program here. We are for this actually for this range here is actually returning a yield, a generator object. So in these squares, you can see we are using we are creating a generator object that will emit some integer values here. So it will return us 3 different values, 0, 1, and 4. And if we assign this yield value of the squares, so what do you expect to be the type of this a here, this variable a here? Is it a list of values? Or what is this object a here? What is this variable a here? Actually, you can we have just seen it in the slides, not in the slides, but in the material here. So it's actually a generator object. So this a here is a generator object. It's not a list of values. And if we want to extract values from this generator object, we have to use the keyword next. So, or we can use a for loop to iterate through this generator object, the items of this object. So what do you expect to see here with this next? With this line of print. So what do you expect to see? Because we are kind of extracting values from this generator. So what is the first value to be extracted for this one? 0, right? Should be 0. But what about this? Inside this loop, if we continue to run this program here, and inside the loop, will we get 0, 1, 4? Or we will only get 1 and 4? 0, 1, 4? Actually, the state of getting next is global. So we will only get 1 and 4. And let's see how this program runs. So you can see inside the loop, we can only get 1 and 4 once we get this next here. However, if we comment out this if we comment out this calling of this next function here, what do we expect to see here in this for loop? We would expect to see inside for loop 0, inside for loop 1, inside for loop 4. So this is what we are going to see here if we don't call the next here. So the status of which value has been visited in a generator object is maintained globally. So this is roughly the mechanism of yield for Python, and we are using it here in PyTest to use the feature that yield will not terminate the control flow of the current function, so that we can still run the teardown code after yielding the result. So if inside the fixture you don't need a teardown, for example, you just want to create that file, but you don't want to remove it, and then you can use return. But if you want to have some teardown code, you have to use yield here inside the fixtures. So that's the basic idea here. And you can inside in PyTest, inside of one fixture, you can use unlimited numbers of returns, because return will terminate the execution of the current function. So it doesn't mess up the control flow of the entire program. But if you use yield, you can only use exactly one here, because otherwise the text which is using the fixture will be confused. It won't know which object to use inside the actual test. So for the number of times point of view, we can use many returns, but we can only use one yield. And the return here is, so this is a little bit different. The behavior is a little bit different from the Python's behavior. So in PyTest, in return, if you use return, it's the same as how it works in Python. So you just get whatever it is returned. But if you use yield, you are not getting an generator object here in the test. So you can see that we just use the fixture here, the return, the yielded value here, the same way as if it is a path, right? As if it is a path. So we are not using this one here as a generator. We are not using next to extract values from this thing here, right? So this behavior is a little bit different from the default behavior of Python. So in PyTest, what we get from this yielded value is actually the expression of this thing here. So we just got whatever the value of this expression is instead of a generator. So this is a little bit different from the behavior of Python. And if we just use return, we will have no chance to do tear down. And if we use yield, we can do the tear down process after the yield statement. So this is roughly how it works. And if you wonder how the process is like, it actually works like this. So we just run the setup code inside the fixture, and then we yield the value, and then the control flow is passed to the test function. Then the test will just run, and then we will get back to the logic. The control flow will be passed back to the logic of the fixture to do the teardown. So this is how the control flow works in this case. And you may see that we can see this small notation here. The first test needing this code, needing the fixture is doing the setup. Actually, this is because fixtures, as we have learned here, is used to create reusable resources that could be shared among different tests. So once we have created this fixture of file, this temporary text file, we can use it in multiple tests. We can use it across different tests, and only the first test using this fixture is doing the setup here. So that's the case here, and because multiple tests could be using the same fixture, so we can have scopes for fixtures to allow only certain tests to see this fixture here, and we can have several different levels of scopes. We can have function level, we can have class level, and module level, package, or session level. So this is from the lowest level to the upper. This is the order here. So basically, by default, the scope is a function. So only a function can use a scope. However, we can also specify the scope to be a class. So inside the class, everything can use this fixture here. And for modules in Python is like each directory or each folder is like a module. And for package is like a group of whatever you have installed using pip is actually package. So a package is like a collection of different modules, different folders, different individual files. And a session is like this fixture could be usable for all the packages which are involved for running this session of testing. So these are the different scopes. And we can also, there's another feature of fixture which is called auto use. So if inside I think the screen is a little bit blurred, can you see it clearly? So maybe you're not seeing it at all, but the thing is, using in the annotator of the fixture, we can specify this. We can specify this auto use parameter. We can set it to be true to make sure that to make sure that every test can use this fixture. So by default, we have to, maybe I need to enlarge this. So by default, if we want to use a fixture, we have to specify the name of the fixture in the test that is using the fixture. However, if we set auto use to be true, then we don't need to specify the fixture name here. We can use it directly inside the code. So that's the usage of this auto use flag. And this is not encouraged to use. This is just to let you know there's such a thing, but normally we don't use it because it will mess up the readability of your code. So that's the thing here. And actually that's all about fixtures. And fixtures is more like, if we come back to our previous lecture about test scaffolding, it is more like what we used for a driver of the program. So basically it's driving the entire testing process. And before we end this lecture, let's learn one more concept for PY test, so which is called parameterization. So when we write tests, and maybe it's better to share the PDF files for this one, so you can have a clearer look. So this looks better. So in many cases, when we write a test, we may want to have many constant values as our test cases and the assertion values, right? So for example, when you were in your assignment 1, when you create those test cases, those are like constant values, right? We have maybe for one function that is being tested, we have a list of constant values as test cases here. And if we do a white box testing, if we don't have the feature of parameterization, we will need to write multiple pieces of unit tests holding each collection of constant values, right? So this parameterization actually solves the problem of rewriting tests for different constant test cases. So what you can do is you can parameterize different values here and then assign values using this parameterized grammar here. So basically you just have a string as the first parameter, which is used to indicate the names of the variables you are trying to parameterize for your test. And then you have a list of tuples, and each tuple is actually a set of constant values to be passed as the parameters here. And the parameter values could be used as variables of running the test or the assertion values here. So this is parameterization. It is very good for you to write clean code when you have multiple test cases with constant values. So this is a very useful feature. And maybe let's skip let's leave this for the next lecture, and let's end today's lecture now. And thank you for coming. And if you have any questions regarding to marks or for your assignment 1, you can come to our course admins here. And if not, that's the end of today's lecture. Thank you.